On the 4th of May 2026, a paper appeared in Nature Astronomy. Its lead author was Ben Forrest, research scientist at UC Davis, part of a survey called Magazine. The paper described a galaxy. Designation: XMM Vide 1 2075. It formed less than 2 billion years after the Big Bang. It contained several times more stars than the Milky Way. It had already stopped forming new ones, and it did not rotate. Not slowly, not imperfectly, not with a wobble or an offset axis. The data showed no ordered rotation at all, only random motion, stars drifting in no direction, with no shared angular momentum, orbiting nothing collectively. Science has a name for this kind of object. The name is slow rotator. The name is not an explanation. This is not a story about a galaxy that doesn't spin. This is a story about what happens when the foundational assumption of an entire field of physics, the assumption that galaxies rotate because that is what galaxies do, encounters an object that refuses to comply. This is a story about angular momentum, about the force that should have set every galaxy in motion from the moment of its birth, about what it means when that force simply isn't there. And this is a story about a name, because the word we use, slow rotator, describes something that takes 12 billion years to achieve. XMM Vid 1 2075 did it in under 2. The word doesn't fit. The phenomenon doesn't fit. And right now, nobody has a better one. To understand what's wrong with the galaxy known as XMM Vid 1 2075, you first have to understand what's right with every other galaxy we've ever observed. It begins with a simple, elegant idea about how the universe organizes itself. In 1969, long before we could simulate cosmic evolution in detail, Jim Peebles proposed that galaxies acquire their spin through tidal torques. Imagine the early universe, a vast, almost uniform sea of gas, but with tiny, random fluctuations in density. Gravity amplified these overdensities, pulling matter into clumpy, protogalactic clouds. As these neighboring clouds pulled on each other, their mutual gravity wasn't perfectly symmetrical. This imbalance exerted a twisting force, a torque, imparting a gentle, large-scale spin. The gas that fell into these forming galaxies carried this angular momentum with it. Gravity pulled it inward. Conservation of angular momentum flattened it into a disk. The disk rotated. This is not a hypothesis. This is the foundational mechanism. Tidal torque theory has been confirmed by decades of supercomputer simulations, by direct observation, by the rotational signatures of thousands of galaxies. The prediction is simple and universal. Galaxies form. Galaxies spin. The spin is inherited from the cosmic environment that birthed them. It's a galactic birthright. In the 1970s, Vera Rubin measured the rotation of galaxies with unprecedented precision. She discovered that spiral galaxies don't slow down at their edges, as Newtonian physics would predict. The rotation curve stays flat. Stars on the outer rim orbit at the same speed as stars near the core. This should not happen unless there's a vast amount of mass we cannot see, extending far beyond the visible stars. That discovery gave us the modern concept of dark matter, but it also reinforced something deeper. Rotation is not optional for galaxies. It is structural. It is how they exist. Flat rotation curves prove that even the outermost stars, the ones barely held by gravity, still orbit, still move in order, still spin, tethered to the unseen halo that governs their motion. The Magaz-3 survey, Massive Ancient Galaxies at Z greater than 3, near infrared, was designed to find the most extreme galaxies in the early universe. Led by Gillian Wilson at UC Merced, with key contributions from Ben Forrest, the team used the powerful W.M. Keck Observatory in Hawaii to identify targets. One of those targets was XMM Vid 1 2075. Keck confirmed the basics. This was one of the most massive galaxies ever seen in the early universe, containing several times the stellar mass of our own Milky Way. And it was already quiescent. It had stopped forming stars. In a universe less than 2 billion years old, this galaxy had already lived its entire productive life and gone silent. That combination of extreme mass and premature death made it a compelling target for the James Webb Space Telescope. Ben Forrest and the team pointed JWST at XMM Vid 1275 and two other galaxies of similar age. They used the telescope's near-infrared spectrograph, or NIR spec, to measure how material moves inside each system. This works by analyzing the Doppler effect in the galaxy's light. If a galaxy is rotating, one side is moving towards us, and its light is compressed to shorter, bluer wavelengths. The other side is moving away, its light stretched to longer, redder wavelengths. A map of this light reveals a clear red to blue gradient. That's rotation. If there's no ordered motion, the wavelength is uniform across the entire galaxy. That's stillness. Of the three galaxies observed, one showed clear, ordered rotation. The kind you expect, the kind every model predicts. Another was what Forrest called kind of messy. Some rotation, some disorder, the signature of a galaxy still organizing itself, perhaps in the aftermath of a recent merger. And the third, XMM Vid 1275, showed no rotation, no ordered motion, no angular momentum signature at all. Just a chaotic swarm of stars moving in random directions inside a massive, dead structure. Its motion was dominated by dispersion, like a swarm of bees in a box, not a spinning disk. Forrest said, "That's consistent with some of the most massive galaxies in the local universe, but it was a bit surprising to find it so early on." A bit surprising. An observation that quietly contradicts the most fundamental rule of how galaxies are supposed to be built. Here's the thing nobody talks about. In the local universe, the one we can see around us right now, there are galaxies called slow rotators. Giant elliptical structures with no net spin. Their stars don't orbit in a neat flat plane like our own Milky Way. Instead, they swarm like bees in a hive, moving in random directions inside a massive gravitational well. No disk, no spiral arms, no ordered rotation. This is a fundamental state of galactic structure, as different from a spiral as a sphere is from a frisbee. These galaxies exist. They are real. Their existence is not the mystery. The mystery is how long it takes to make one. Current theory, backed by decades of simulations, says a slow rotator is the product of repeated mergers. It's a process of cosmic attrition. Galaxy after galaxy crashes into the structure over billions of years. Some collisions add spin, nudging the whole system one way. Others, arriving from a different angle, cancel it out. Over time, over 13 billion years, the net rotation approaches zero. The stars lose their shared direction. They drift. The galaxy becomes what scientists call a slow rotator. This process requires time, enormous amounts of it. It's a chaotic, inefficient path to stillness. Multiple mergers across cosmic epochs are the key ingredient. The slow rotators we see nearby, in the local universe, are old. They are the galactic elders, having had the full lifetime of the cosmos to settle into this state of gravitational equilibrium. XMM Vid 1275 reached it in under 2 billion years, not because it had more mergers. There simply hasn't been enough time for a long chain of multiple mergers in a universe less than 2 billion years old. The cosmos was too young, galaxies too spread out. Not because it evolved faster. Evolution doesn't skip structural phases. The laws of physics are constant. But because something else happened, something the models didn't predict. Forrest and the team have one hypothesis: a different path to stillness. Not multiple mergers canceling rotation over eons. A single catastrophic collision. Two galaxies, spinning in nearly opposite directions, crashing into each other. If Galaxy A rotates clockwise and Galaxy B rotates counterclockwise, and they collide, their angular momentum cancels. Not partially, almost entirely. In one violent event, the shared spin of two massive structures is destroyed. The ordered motion is converted into the chaotic, random energy of a pressure-supported system. Forrest said, "For this particular galaxy, we see a large excess of light off to the side. And so that's suggestive of some other object which has come in and is interacting with the system and potentially changing its dynamics. The light is there. The object is there. The evidence points to an interaction. The collision may have happened. But here's the detail that stopped me when I read it. The part that elevates this from a curiosity to a profound challenge. If this hypothesis is correct, if a single counter-rotating collision killed the spin of XMM Vid1 2075, then the collision had to be nearly perfect. Think of it as a cosmic billiard shot of impossible precision. Two galaxies spinning in almost exactly opposite directions, with almost exactly opposite angular momentum magnitudes, hitting each other at the right angle, at the right speed, with the right mass ratio, to cancel rotation to within the precision that JWST can measure. Not close to zero, measurably zero. Any significant deviation in mass, speed, or angle of approach, and the resulting galaxy would still have some residual spin. But this one doesn't. That's not a collision, that's a cancellation event. And the probability of it happening by chance, of two galaxies finding each other with precisely opposing spins in a universe less than 2 billion years old, is a number that nobody in the paper calculated. Because the number might not be comforting. It suggests an event so rare, it borders on the impossible. And XMM Vid1 2075 is not the only galaxy JWST has found that refuses to behave. It's not an isolated data point. It's part of a pattern. In the past 2 years, JWST has systematically demolished the timeline of galaxy formation. It has delivered a steady stream of uncomfortable facts. Galaxies too massive for their age, challenging how quickly structure can form. Spirals that formed before spirals should exist, questioning our models of disk stability, black holes that grew faster than physics allows, forcing us to rethink accretion, an expansion rate that gives two different answers depending on how you measure it. And now, a galaxy with no rotation in an era when everything should be spinning. 3 days after the XMM Vid1 2075 paper, another team published results on a galaxy they call the Big Wheel, at redshift 3.2, roughly 11.5 billion years ago. This galaxy is a disk. It rotates. But its size is almost 3 times larger than expected for galaxies of similar mass at that epoch. Its stellar-to-halo mass ratio is far higher than models predict. It assembled its stars with an efficiency the general population doesn't achieve. It's an overachiever, a galactic prodigy that grew too big, too fast. 2 galaxies, 2 papers, 3 days apart. One that stopped spinning far too early, another that grew far too large. Both doing things the models say they shouldn't be doing yet, both pointing to a gap in our knowledge. The universe is not broken. It is behaving exactly as it should. But our understanding of it, the story we tell ourselves about how it all works, might be. The angular momentum problem is not new. It's a persistent, low-level hum in the background of cosmology. But with the discovery of XMM Vid1 2075, that hum has become a piercing signal. The problem is now acute. The standard model for how galaxies get their spin is called tidal torque theory. It posits that galaxies acquire rotation from their environment. Imagine the early universe, a vast web of dark matter and gas. Overdense regions destined to become galaxies don't collapse in perfect isolation. The gravitational pull of neighboring structures, filaments, voids, and other proto-galaxies is uneven. This asymmetry creates a torque, a twisting force that spins up the forming galaxy. This happens early in what's called the linear regime, before the galaxy fully collapses. The spin direction and magnitude are set by this initial cosmic dance. From that point on, the law of conservation of angular momentum takes over. This spin doesn't just go away. It can be redistributed through mergers. It can be modified by interactions. But the total angular momentum of a galaxy and its dark matter halo is a conserved quantity. It cannot be created from nothing, and it cannot be destroyed. Cannot. And yet, XMM Vid1 2075 has none. Not reduced, not diminished, not redistributed into a different axis. None. Measurable zero. Within the tight constraints of the observation, the galaxy is perfectly still. What drove the complete cancellation? What happened to the angular momentum that tidal torques should have given this galaxy at birth? And if the single collision hypothesis is the answer, what are the odds of such a perfect, spin-erasing impact? Dark matter complicates this further. Vera Rubin's flat rotation curves proved that galaxies spin faster than their visible mass allows. Dark matter halos provide the extra gravitational grip. The halo and the disk are dynamically coupled. They rotate together, their angular momentum linked. If XMM Vide 2075's stars have no ordered rotation, what about its dark matter halo? Did the collision cancel the halo's spin too? This is a critical question, as the halo contains the vast majority of the system's mass and angular momentum. Or does the halo still rotate, dragging invisible mass through invisible orbits, while the visible galaxy sits motionless inside it, a ship becalmed in a spinning sea? The paper doesn't address this. The data can't address this. JWST measures light. Dark matter emits none. We can only infer its presence, not observe its motion directly. Forrest noted that some simulations do predict a very small number of non-rotating galaxies very early in the universe. But these models are complex with their own caveats. They rely on subgrid physics, approximations for processes like star formation and feedback that are too small to simulate directly. A result like this pushes those approximations to their limits. The team is now searching for more examples to determine whether XMM Vid 2075 is an anomaly of 1 or the first member of a class we didn't know existed. If they find more, if the early universe contains multiple galaxies with zero rotation, then tidal torque theory, the foundational mechanism of galaxy formation, has a gap, a structural omission, a scenario it cannot account for, suggesting our understanding of the initial conditions of the universe is incomplete. If they find only this one, then XMM Vide 2075 is a statistical miracle, a near-perfect cancellation event, an accident of such precision that it borders on the implausible, a cosmic coincidence of the highest order. Either answer is uncomfortable. One implies a flaw in our theories. The other, a profound statistical fluke that challenges our sense of a predictable, orderly cosmos. We can test these simulations and really figure out how common they are, and that can then give us information about whether our theories of this evolution are correct. Translation: we don't know yet. The data is insufficient. The models are untested at this extreme. The name we gave it, slow rotator, describes a process that takes the age of the universe. This galaxy completed that process before the universe was out of its infancy. It presents a finished puzzle, but we have lost the instruction manual for how it was assembled. Imagine you are a star inside XMM Vid 2075. You formed less than 2 billion years after the beginning of everything. Around you, billions of other stars, several times more than the Milky Way contains. But none of them move with you. None of them share your direction. You have no orbit, no axis, no center to revolve around. You drift. The galaxy that holds you is massive. Its gravity binds you. But its gravity does not guide you. There is no disk to flatten your path, no spiral arm to channel your motion, no rotation curve to set your speed. You move because something pulled you in. But once inside, you are untethered, random, disordered. Around you, star formation has stopped. No new stars ignite. No gas collapses into protostars. The fuel is gone. The galaxy is massive and dead, finished with creation before the universe finished its 2 billion years. You are inside something that should not exist. Not because massive galaxies are impossible, but because a galaxy this massive, this motionless, this early, has no pathway in the models, no mechanism in the equations, no name in the literature that actually explains it. You are a star inside a structure that the universe does not have the right word for. XMM Vid 2075 sits in the early universe, less than 2 billion years after the Big Bang, several times the stellar mass of the Milky Way. No star formation, no ordered rotation, no angular momentum. We named it a slow rotator, but that's not quite right either, because slow rotators are slow. They take time. This one didn't take time. It arrived at the destination before the journey should have started. We named the collision hypothesis. Two galaxies, counter-rotating, canceling each other's spin in a single event. It fits the data. The excess light is there, the dynamics allow it. But the precision required, the near-perfect opposition of spin, magnitude, angle, and mass, is a number we have not calculated. Because the calculation might reveal that this galaxy is not a product of probability. It might reveal that it is a product of something our models do not yet contain. Ben Forrest and the Magaz-3 team are continuing the search. More targets, more observations, more data to test whether this galaxy is alone or whether the early universe contains others like it. Massive, motionless, unnamed. The simulations say they should be rare. The simulations also say the universe should not contain galaxies this massive at this epoch. JWST has already proven the simulations wrong on the mass question. It may prove them wrong on the rotation question too. The universe contains something for which we still do not have the right words. A galaxy that achieved a state models require 12 billion years to produce, in under 2. A structure that canceled its own spin with a precision that borders on impossible. A massive dead object sitting motionless in the earliest epoch we can observe, while every neighbor rotates. We named the parts we could explain: slow rotator, tidal torque, angular momentum, dark matter halo. But there is one portion of this discovery for which we still cannot find the right word. The portion where the rules stop. If this is the kind of story you're looking for, real science, real missions, real phenomena that still have no name, subscribe to Orbitalis. The next video is already in motion.